As we've seen, it's not merely the size of a telescope that's important. Of equal importance these days are the instruments which astronomers use on them.
I remember going to Palomar in the early 70s with a new detector which I'd called the image photon counting system, putting it on their spectrograph. Previously they'd used photographic emulsion, and overnight the power of the telescope went up by a factor of 1,000. This was only due to the detector. The spectrograph was the same and the telescope was the same. It was just that detector that was different. Now of course one finds that you need to improve the instrumentation. The instruments that generally are made have several optical elements in them, and the light reflects from one to the other, and some loss occurs at each reflection. So the next stage was to try and make instruments which have the fewest number possible of reflections, and some of those indeed were made. But of course that's not enough yet. Having the very good detectors, having a very good instrumentation, one still needs a very good sight.
The first outpost was on top of an extinct volcano in the Canary Islands, the Rock de los Muchachos, the Rock of the Boys. These rocks are the boys, and I'm quite sure there must be some kind of a legend about them, but I've never been able to find out what it is. This is the INT, or Isaac Newton telescope, originally set up in Sussex, but then transferred to La Palma, where the seeing conditions are much better. It is, of course, fully computerized, and is set up on a conventional equatorial mounting, so that when the telescopes move east or west, the up or down motion of the target looks after itself. But this is not true of what is now Britain's largest telescope, the WHT, or William Herschel telescope. It has a 165-inch mirror, but the mounting is alt-azimuth. This kind of mounting was pioneered in the 1970s by the Russians, with their 236-inch reflector built in the Caucasus Mountains. Optically, the Russian telescope never has been a success, but the mounting set a new trend that's been followed by almost all major telescopes ever since.
The principal advantage is that it's a more compact design, there's less metal to move around, and it's therefore a cheaper telescope to build.
Then why wasn't it used before?
It's a more complex telescope to control. Wasn't possible to control an alt-azimuth telescope effectively before the age of computers.
What are the main lines of research carried out here?
Well, the Herschel telescope is intended to be a general purpose research facility. There's a very wide range of instruments, including imaging CCDs, spectrographs with low, intermediate, very high dispersion. There's an infrared camera, multi-object spectrographs. And that range of instruments allows us to cover a whole range of astronomical research, essentially from comets to cosmology, and most of these subjects in between.
What about future plans for La Palma?
Well, for the Herschel telescope, the major new development is the adaptive optics program, whose goal is to correct for the effects of atmospheric seeing. And more generally, we also have the Italian Galileo telescope arriving on La Palma, which will be another telescope of the same sort of class as the Herschel telescope.
La Palma is a Spanish island, but it's a truly international site, and there are telescopes of many nations here. Among others, the Carlsberg Transit Instrument, the Swedish Solar Tower, the telescope named after the Dutch astronomer Jacobus Captain, the Nordic telescope. Here on the rock, we are more than 7,000 feet above sea level, but there are observatories much higher up than that. At over 10,500 feet here in Arizona, there is Mount Graham, well away from any light pollution and an excellent site for a major observatory. But the astronomers have reckoned without the local squirrel population.
You have to envision the mountain as being like an island rising up in the midst of the desert. It's called a sky island. And so the squirrel has been here for many years, isolated from its brethren on other mountains, and so developed a subspecies of its own up here.
Are they really endangered?
Yes, they are, because there's such a small number on the mountain. But we've found that since our construction has started and our telescopes here, their numbers have increased year by year. So we feel that the telescopes don't affect them one way or another.
The telescope being built here is the LBT, or Large Binocular Telescope. It'll have two 8.4-meter mirrors. What are the advantages of a twin telescope over a single mirror one?
Well, there are two main advantages. One is that you've got more collecting area, twice as much collecting area as a single telescope. And that secondly, you've got much more resolution of detail, because you've got a greater distance between the edge of one telescope mirror and the far edge of the other mirror. So you've got more resolution.
When will the LBT be fully commissioned?
Good year to remember, 2001. That's the aim for first light.
High though Mount Graham is, there are observatories at still greater altitudes. One is Mauna Kea in Hawaii. Mauna Kea is an extinct volcano, at least I hope it's extinct, and on its summit are some of the world's best telescopes. The altitude is 14,000 feet, so you have to be careful how you move around. You're taking in only 39% of your normal oxygen intake. Britain has various telescopes here. One is UCAT, which is mainly an infrared telescope. This has a 150-inch mirror, but there is a limit to the size in which you can make single mirrors, so when a really vast telescope was decided upon, it was planned to use a segmented mirror. The result was the Keck Telescope.
Early on, I decided, this was a long time ago, back in 1977, I decided that it would be interesting and valuable to the University of California to design a 10-meter telescope. And so I looked into ways we might build a telescope of that size, and I rapidly came to the conclusion that a monolithic mirror, that is a single piece of glass for the primary, would not work at this size. That's the way virtually all other telescopes have been built. And I decided that was impractical due to the difficulties in acquiring the glass and in properly supporting it. And the alternative then was segmented. And we've been building mosaic floor tiles for many, many centuries, and so the idea of making a mosaic is not novel at all, of course, but it is novel to astronomy.
What were the main design problems?
The main design problems were the active control system that's required to position all those independent segments so they act as though they are one continuous mirror, and the process of polishing those mirror segments.
That's not the end of the story. Two telescopes are always better than one, so Keck 1's now been joined by its twin, Keck 2.
Keck 2 is doing extremely well. It went into operation just last October, and already it is being used by scientists from all over the world to do some extremely interesting faint object work.
What are the main advantages of having a second telescope?
Well, I think the obvious advantage is that the demand for one telescope of this size is so high that having a second one at least allows you to meet some of that demand, a little more of it. But there are a number of other advantages, of course. In the long term, it will allow us to use the two telescopes together as a single unit.
What are the main results carried out so far?
There are a number of them. Some of the most exciting include a very deep image of using the low-resolution imaging spectrograph with Keck 1, the deepest image ever taken of the universe from a ground-based telescope. And secondly, some speckle imaging results of some of the moons of Jupiter, and in particular Io. We actually captured a volcanic eruption on Io using the Keck, so we had that kind of resolution with the speckle use of the telescope.
The Kecks have 10-meter mirrors, and that's huge. Is it possible to make still larger telescopes, do you think, of this kind?
I think it is certainly possible. I mean, we can expand this technology. The mirrors are a manageable size. There's no obvious reason why one couldn't continue to make bigger and bigger telescopes on the segmented mirror approach.
As you can see, the Keck telescopes are side by side. It's quite different with the Gemini telescopes. They're not side by side. They're not even in the same country. And their mirrors are single, not segmented. Newton's first reflector had a mirror 1 inch across. Each Gemini mirror is 325 inches across. Just outside Paris, the first one is being ground and polished. This one will go to Hawaii, the second to Chile. Working together, each with a 325-inch mirror, they will be immensely powerful.
Well, they're two of the best sites in the world. They're very high, so it's very dry, and the astronomical seeing is superb at both sites. And so we've chosen one in the northern hemisphere and one site in the southern hemisphere.
Obviously, this is very much an international project, and Britain has been concerned.
Britain's played a major role in the project right from the very beginning. It's a 25% partner, and it's been building some of our major components.
What are the main goals of Gemini? I know that's a big question.
Well, there are several goals, but the two principal goals. First of all is to have two telescopes so we can cover both hemispheres. And the second is to achieve exceptionally good image quality, so we can actually make images at infrared wavelengths of the same quality that you see with the Hubble Space Telescope, except we have an 8-meter mirror which to make these images. We've used a meniscus mirror, which is essentially a 22-ton contact lens shaped mirror made of a very special glass that allows the mirror to be polished to an exceptional accuracy, which is basically equivalent to, if you imagine our whole 8 meters spread over the Atlantic, At no point must there be a wave higher than an inch, which is a very, very smooth mirror. You can probably make larger single mirrors, but I think it's difficult to actually make telescopes and to transport these mirrors around the world.
So Gemini is one of the new generation of 8-meter telescopes. But there have been other ideas for coping with the giant mirror problem. For example, the MMT, or Multiple Mirror Telescope in Arizona, used 6 72-inch mirrors working together, and the result didn't look much like a conventional telescope. However, the 6 mirrors are now being replaced by a single, literally revolutionary mirror. Underneath the University of Arizona football stadium, there's a most unusual astronomical laboratory. It's here that the great new mirror for the telescope is being built, 6.5 meters, or 256 inches in diameter. For this method, everything depends upon a really effective furnace. It can attain a temperature of well over 2,000 degrees Fahrenheit, and it can spin at up to 10 revolutions per minute.
The idea of spinning is very simple. If you take a pool of liquid, whether it's water or glass or whatever, and you spin it around, then the liquid gets thrown to the sides, and so you form the dish shape that you want for a mirror. But the more difficult problem we had to solve is to make honeycomb structure. So there are two things going on at once when we make the mirror. We spin the liquid glass. We also fill the liquid glass with blocks of material that will later be removed to make cavities. And it's learning how to do that that's actually been more difficult. It's actually about 2.5 feet thick, and of that thickness, 80% of it is air. So if we melted it, it would actually only be 6 inches thick.
Also in Arizona, there is the Kitt Peak Observatory, America's national observatory. Domes sprout all over the mountain, but dominating them is this extraordinary-looking solar telescope. The sun's light is caught at the top by the coelostat and diverted down the tunnel, where it's guided into the laboratory below for analysis. Of course, Kitt Peak has great optical telescopes too, such as the 4-meter reflector, which is a virtual twin of another 4-meter in Chile. Good though the Arizonan skies are, there are even better sights in the Atacama Desert of Chile. At Cerro Tololo, we find the sister telescope of the Kitt Peak 4-meter reflector. Rather further north is Las Campanas. From here, in 1987, an astronomer discovered the supernova in the Large Cloud of Magellan. And close by is the European Southern Observatory at La Sierra, again with the most modern equipment. Among its telescopes is the impressive NTT, or New Technology Telescope, in the new type of building, which makes it possible to keep the images really stable and clear-cut.
The building is built around the telescope, and this of course gives a couple of problems. Indeed, since you can turn the building eternally, you have to take in all the electrical power by slip rings, but this has been done and it also works very well. Everything is done by computer. There are a number of features in this telescope which are entirely new, and the first one, and I think the most obvious, is that the telescope is smaller and the building is smaller. This is done so because we want the air around the telescope to be more stable, to be more quiet, and therefore the images will be more sharp. Another one, and I think perhaps the most important one, is that this telescope incorporates the new concept of active optics. That means that the main mirror, which is 3.6 meters in diameter, is actively controlled by a computer. It is a rather thin mirror and therefore also rather light, and it would flex if we just left it all by itself. But it is supported by 78 supports which are computer controlled, and by watching the image of a star all the time, we can actually correct the shape of the mirror so that this image will always be as sharp as possible.
But astronomers are never satisfied, and new observatories are being planned. At Cerro Paranal, in the northernmost part of the Atacama Desert, the European Southern Observatory is building the VLT, or Very Large Telescope, and this will have 4 single 8-meter mirrors working together.
The VLT is built to operate as a single machine, and in this place the light gets brought from the 4-unit telescopes through a maze of tunnels and gets combined in an incoherent way to give us an equivalent aperture of a 16-meter telescope. These are the ports where the light gets diverted to. And here, Patrick, we have the interferometry tunnels. This 136-meter long tunnel allows you to combine the light from the 4-unit telescopes and the 3 auxiliary telescopes into a coherent light beam. In here, we have mounted on railway tracks little trains, and on those trains we mount mirrors. By moving the train backwards and forwards, we can delay the time of arrival of the light, such that all telescopes seem to be operating as a single unit. In this mode, the telescope operates as a 120-meter mirror with an angular resolution of 0.001 arcsecond, 1 milliarcsecond.
But even at a site as good as the Atacama Desert, we are still deep inside the Earth's atmosphere. To improve matters, we must go still higher. A partial solution is to use a jet aircraft, and this has been done with the KAO, or Kuiper Airborne Observatory, named in honor of Gerard Kuiper, the Dutch astronomer who was a pioneer in this kind of research.
The main purpose for the KAO is to do infrared astronomy. And in order to do infrared astronomy, you have to be above the water vapor in the atmosphere. So by flying at high altitudes, we typically fly from 39 to 45,000 feet. We can do that and conduct infrared astronomy. And secondarily, our mobility is key because it allows us to move the airplane and the telescope around the world to put ourselves in the optimal position for special events such as eclipses, stellar occultations, and southern sky observations.
How do you keep the telescope sufficiently steady?
What we do to isolate the telescope is we have the telescope housing sits on 4 vibration isolators, which serve as shock absorbers for the telescope and remove some of the vibration from the aircraft. We also have the telescope balanced on a 16-inch spherical air bearing, which allows the airplane to rotate around the telescope, allows the telescope to stay steady while the airplane moves around it.
Even the KAO is not above the whole of the atmosphere. The only way to deal with that is to go right into space, and it may not surprise you to know that this has in fact been done with the Hubble Space Telescope, run from the Institute here in Baltimore. The telescope was launched in 1990, initially with a 40 mirror. That was put right with a service commission in 1993, and since then the telescope has sent back amazing results.
If we can start from the most distant objects that we have observed, is what we call the Hubble Deep Field. These were observations of a very empty space of the universe, only as large as a grain of rice held at the distance of my arm. And in that very small piece of the sky, we discovered about 3,000 galaxies. Galaxies which were not known before, very few of them had been observed from the ground. And what this tells us is that if we multiply that small area of the sky by the whole surface sphere of the sky, that there must be about 80 to 100 billion galaxies in the universe. So to us, that was a major discovery. The Hubble Space Telescope has made major inroads in our understanding of how stars themselves are being formed. Observations of such objects as the Orion Nebula or the M16 Eagle Nebula has shown a large number of stars that are being formed out of these condensations of gas and dust. And it's very exciting to see that in many cases, around each of those stars, we have protoplanetary systems that are being formed. In more than half of them, we'll see these protoplanetary systems. And so we would expect planets to be commonplace amongst the stars that are being born today and those that were born in the past.
Things are happening all the time. Are there any very important recent discoveries?
Well, it's very interesting that over the last month, a number of satellites have pointed at what they call a gamma ray burst. These are objects in the sky which we really do not understand. They were discovered by gamma ray satellites. They produce an enormous amount of energy, but the resolution, the precision with which gamma ray satellites can point in the sky is so imprecise that we cannot really know what the objects are that are emitting this enormous amount of lights. The new BeppoSAX, an X-ray satellite, Italian-Dutch satellite, discovered this source just over a month ago. Ground-based observations and observations with other satellites were able to pinpoint the location to a sufficient accuracy that we could make the first observations with the Hubble Space Telescope about a month after the initial discovery. More observations are ongoing, and what we expect these observations to tell us is whether these gamma ray burst sources are objects within our own galaxy, and there are theories that would explain it that way, or objects that are in external galaxies.
I must ask you this. What about comet Hale-Bopp?
Bright comets such as Hale-Bopp were first discovered from the ground, but observations of Hale-Bopp occurred well over a year ago, and more will be forthcoming. And hopefully through those observations we'll be able to understand how the comet is made of, what is it made of, how does it behave from a dynamic point of view around the sun and in our solar system.
I know this is difficult to answer, but can you forecast what the Hubble telescope may tell us in the next few years?
One of the fundamental programs, of course, the reason for what we call the Hubble is to measure the Hubble constant, which is the velocity by which the universe is expanding. We are well in our way to get that number, and that number is very important because it tells us not only how fast the universe is expanding, but it's one of the two numbers that we need in order to say whether the universe will continue to expand forever or fall back in itself, and also is the number that tells us how old the universe is.
We began this anniversary program at my modest observatory in Chelsea, so perhaps it's fitting to end here. And the story of the telescope is indeed a remarkable one. It's taken us from the primitive optic tubes of pioneers such as Galileo through to the giant instruments of today, such as the Hubble Space Telescope. And where's it going to end? I wonder, what about the 80th anniversary of the Sky at Night program? Will my successor be able to talk to you from a space station or the surface of the moon? Quite possibly. I won't be here, but some of you now watching this program may well be. And of one thing we can be quite certain, whatever happens, it's going to be exciting. The story of the telescope is far from over. Indeed, it may only just be beginning. Good night.